Hi, thanks for introduction. Hello, can I do this? Yeah, hello everyone. My name is Qijing. So, as Surya said, I just graduated from UC Berkeley working with Michael Jordan. And now I'm in IES. I'm also joining as assistant professor at Princeton University. And I've been working a lot on non-convex optimization. Today I would like to share some of my recent interests in the exploration of the reinforcement learning. And I guess this is the last talk of the day, and also this is a deep learning workshop. So I will try to be light on the techniques, and if you're really into a lot of technical details, please look into our papers. So first, about reinforcement learning, I think the framework of reinforcement learning is actually trying to solve a bigger problem, which is called a sequential decision-making problem. Just like AlphaGo is trying to solve this Go problem. In a sequential decision making, you are not only involved in just making one decision like at a time. You actually want to make a sequence of decisions, and you can adjust your decision based on the previous feedback you have. As we said, the framework is reinforcement learning, and there are a lot of popular algorithms these days about how to solve reinforcement learning. A lot of them you know about deep reinforcement learning, like deep Q-learning and policy gradient, but a lot of them is actually really just based on a very classical algorithm called value iteration, Q-learning, and policy gradient, those three algorithms. Yeah. And so let's talk more about the framework of reinforcement learning. People usually talk about reinforcement learning in a setting we call it a Markov decision process. Just imagine we're playing these chess games. So we both have agents and environments. And every time agents is trying to pick an action, like in here, just we how to move each pieces, and we interact with the environment. And the environment will feedback you the next states, and which just the position of each pieces, and then rewards. So in this game, rewards essentially after you're playing all the games, and if you win, you receive reward is 1, and if you lose, you receive rewards is 0, and you don't receive any rewards in the entire course of the game. So we summarize it into the Markov decision process, and which have this many components. The first one is the set of states and also the set of action. And H here, let's just assume the game we talk about today is always an episodic game. That means we always assume the game kind of like ends in 100 steps or some fixed length, which is H. And there are two components which is very important about this reinforcement learning. The first one is the transition probability. That means start from one particular state and action, and you take some action, what is the next state you're going to transition to? And the second one is the rewards. For each state, and you pick some action, what is immediate rewards you're going to receive? So those two are most important about the environment. And usually we don't know beforehand about what is those transition probability and what is the rewards. And the goal of reinforcement learning essentially just trying to find the good policy to maximize the cumulative rewards. That means in the long run, you want to play very well in this Go game. Okay, and the interesting problem in reinforcement learning, especially in theory, we're interested is about so-called sample efficiency. Why it's very important? Because in a lot of games currently the applications we do very well, like Atari games or those Mojoko simulator, algorithm already require massive number of samples, usually order of like 1 million, and this kind of takes a very long time to train. And also there are a lot of real tasks like those how to train the robots, and each task they perform takes like 10 minutes, and which is very time consuming. And also for this autonomous drive, and if you just randomly drive your car and you're gonna crash it, and it's gonna be very expensive, it costs a lot of money. So typically the question we're interested in is how many samples does a reinforcement learning algorithm actually needs? And this is a main question we're interested in. Of course, like other than sample complexity, we're also interested in the runtime. So today I'm gonna first talk to you about exploration. I will like first to explain what is exploration in a simple tabular setting, and then we're gonna go beyond to talk about function approximation, what is hot these days. So first, in a tabular reinforcement learning, there's one very important concept we need to talk about that is called a value function. So the value function in words means just expected rewards when an agent plays start from a given state or state action pair. So for example, I give you this configuration about chess, and you can, if you are already an expert, you can roughly estimate it, okay, how about my position, and I think I have some probably like 0.6 chance, like probability 0.6 to win this game. and then probably assign the value of this configuration to 0.6. So in reinforcement learning, there are two types of value function. As I said, it depends on whether I consider start from a given state or given state action. So one is called a v value, which is a function of states, and the other one is called q value, that is start from some specific state action pair, S and A. And given this definition of value, then we can like just naively think how to solve these reinforcement learning problems. There's an equation called optimal Bellman equation. If you don't be scared about these names, it's actually very simple. So we actually know there always exists an optimal policy that optimal policy, the value of optimal policy would satisfy these two equations. The first equation is nothing but just saying if I already knew Q star is the value of optimal policy for each state and action, then the policy I'm going to pick for each state is, of course, just to maximize this value. I just want to pick the action that maximizes the value I have. And then this kind of defines how we have the V star. And then how to define the Q star. And Q star, by definition, is the value I'm going to receive if expected value I'm going to receive if I start from a state and action, S and A. So by definition, it's just equal to the rewards I'm going to receive immediately, that is RSA, and then the expected rewards I'm going to receive in the next steps, or in the future, which is V star H plus 1, the next steps. And once you know those two equations, it's very easy to explain the classical algorithm, the value-based algorithm we're going to focus in today's talk. The first one is called a value iteration. We know the problem about the optimal Bellman equation, why we cannot run it in practice, is because we have this expectation, which is over the entire true transition matrix. Well, in practice, we only collect a finite number of samples, so we definitely do not have access to this expectation. So all we change is just replace this expectation by an empirical version of the expectation, and this gives us an algorithm called a value iteration. And furthermore, the Q-learning is just an incremental update version of this value iteration. So I guess people here are very familiar with optimization algorithm for deep learning. Usually I think of these two algorithms just as a gradient descent for value iteration and a stochastic gradient descent for Q-learning. So one very basic question in reinforcement learning we would like to ask is how many samples does Q-learning need? And the first thing I want to ask is in the tabular setting. So actually there's the one thing actually entirely missing in this picture. This is tell you how you're going to update a value based on if I already collect a lot of data. But one unique feature of reinforcement learning is the agent need to pick action. So we don't actually know how to get those samples. That means in the empirical expectation, how we collect those samples. Take an example, if I'm doing reinforcement learning, I want to do some business, I want to trade over between a lot of islands. Other than just knowing a lot of islands and plan optimally how to do the trading between them, I should also spend some time just randomly explore around. Maybe by some chance, I will discover some entirely new island. And if I do business on that new island, I'm gonna gain a lot of money. So in this scenario, in this case, so in practice, what people do is I just do some epsilon greedy with Q-learning or with value iteration. Epsilon greedy exploration, that means with majority probability, I'm gonna just take the greedy action. That means the action I will take based on the value I currently have. And with some small chance, epsilon probability, I will take some random action, okay? And this random action gonna eventually, like in the limit of infinite samples, gonna guarantee I discover everything. So this gives us a very basic algorithm called Q-learning with epsilon greedy. And for a very long time, this algorithm we know is going to converge to an optimal policy if we have infinite number of samples. But unfortunately, in practice, we never allow infinite number of samples. So we care about efficiency, how many samples we need to find optimal policy. And there are actually a worst case results by Kern and Singh in 2002. It actually says, in worst case, for tabular MDP, it already requires something exponential. And specifically, this is exponential in terms of the length of the game. Like in the beginning, we assume we do episodic MDP, so we assume each game has 100 steps. So this means we need a sample which is 2 to the 100. Okay. So that's also gives us another story, because this is discovered in 2002. So for a very long time in the field, people just feel, okay, maybe Q-learning is not the right algorithm. Maybe we just do value iteration, and this is like something theoretically sharp. But however, we would like to ask a question, because in practice, people do use Q-learning, especially like play a tower game, people do deep Q-learning, and it's actually performing well. So we are wondering, is Q-learning really bad, or is just because epsilon greedy, which is some suboptimal exploration policy? So we'd like to refer to some literature, which is called Bandit, which actually, the entire literature is about how to explore in this scenario. So the multi-arm bandit, basically the problem is just I give you a lot of bandit machine, and you can pull each bandit machine each time, and you will receive a rewards. And I will assume the rewards you receive is a stochastic version of a true mean of each bandit machine. And the task for you is after a lot of trial of different pools, and you eventually want to find a machine which gives you the highest mean rewards. And in the bandit community, there's actually a more sophisticated exploration algorithm called upper confidence bound. And the idea is very different from epsilon greedy, which just blindly try some random action for some small chance. What it says is I first gonna estimate so-called upper confidence bound. That is, estimated the largest possible rewards for each action. So in this case, I have two actions. I have a true mean, which is mu1 and mu2, and I have 4 pools for the first action and 2 pools for the second action. And I'm gonna estimate my largest plausible rewards based on my empirical mean and also the confidence on the uncertainty I have. In this case, because I put action 1 a lot of times, so I think my uncertainty is gonna be less. So UCB 1, the blue one, is my estimation. And action 2 has a green one as my estimation. And the algorithm to put a UCB is just pick the action with the largest upper confidence bound. So you might ask a question, how we combine this Q-learning and UCB? So it turns out this is the theorem we can show. Q-learning with UCB actually able to find an epsilon optimal policy within this number of samples, which is h cubed SA over epsilon square. Here, H is the length of episode. That means the length of game we're gonna play. S is the number of states, A is the number of action. So what this says is, as long as you change this from epsilon greedy to UCB, you overcome the entire problem about you need exponential number of samples. Now everything is polynomial. And furthermore, we have lower bounds, which is just saying for whatever algorithm, not only Q-learning, whatever algorithm, information theoretically you at least need to try h square SA over epsilon square episodes and to find a near optimal policy. If you compare our upper bound and lower bound, you will see the only difference is just 1 H factor. So the implication of this work is also saying the sample efficiency of Q-learning is actually near optimal. Q-learning is not bad at all. Okay. Of course, I want to just remark a little bit, although I'm saying this is just Q-learning combined with UCB, but you need to design this upper confidence bound for this reinforcement learning problem, which is very different from multi-arm bandit, where you only need to consider uncertainty for the rewards. And here you both need to consider the uncertainty of the rewards and the uncertainty of the transitions. And I just want to show what's a big difference between this upper confidence bound and epsilon greedy. And I can just run Q-learning with both of the algorithm, and I run it in a very small Markov decision process, which only have 2 states, 5 action, and the length of game is only 6. And we can see the upper confidence bound is actually able to find an optimal policy pretty fast and then just gain linearly the cumulative rewards. While for epsilon greedy, in order to find optimal policy, it spends a lot of episodes, which is like 10 to the 4th. Finally, I also want to put our results into the context of the related work. It turns out that there has been a lot of work on reinforcement learning, starting from 10 years ago, which study a simplifier setting, which they call it a simulator setting, which also in the literature we say is no exploration. Just because we give you a simulator, you can query any states and action. And those study of exploration actually not happening till very recently, where there actually already a lot of work on the model-based algorithm, like a value iteration, and they also put a UCB on it. And for example, this Azar-Tal algorithm, they actually achieve an optimal, minimax optimal sample complexity in terms of regret. But unfortunately, on the other side, because it's a model-based algorithm, so the space complexity actually scale with what's the complexity to describe the transition matrix, that is S squared and A. On the other hand, for model-free algorithm, which people tend to use in practice a lot, like Q-learning algorithm, we said the only thing we know so far is epsilon greedy exploration combined with Q-learning just going to give you something exponential in terms of H, which is terrible. And there are also some work in 2006, which is they do some delayed Q-learning. However, their regret is their number of samples is actually 1 over epsilon to the 4th, which is much worse than the model-based algorithm. So our Q-learning result is the first one in the tabular setting and model-free algorithm to achieve the near optimal sample complexity and also regret. And we also enjoy the better space complexity. So far we have been talking a lot about tabular reinforcement learning. But in practice, everyone knows tabular is not what we want. So what's wrong with tabular and why we need the function approximation? Just look at these Atari games we can think of. These Atari games, we know at least there's at least like 100 pixels in it. And we can possibly say for each pixels, we have at least 10 value of like colors. So that for each different picture, that corresponds to different states for these Atari games. So we can easily calculate for this game, which is called Space Invader, it has 10 to the 100 number of states. Just remember in a tabular setting, we kind of like saying all the sample complexity is going to be linear in the number of states. This means for these games, we're going to require 10 to the 100 samples, which is never going to achieve in practice. So we really want to deal with the problem in practice that we have enormous number of states, that is really enormous. And what is good about this situation, why we don't suffer from this worst case scenario, is because although some states, like for example, if everything is shifted by one pixel to the left, we know these are 2 different states, but we kind of like have some prior knowledge. We know those 2 states are kind of like very similar. So we should not just treat it entirely differently. So the way we want to think about it is because there are enormous number of states, but a lot of states actually very similar. So we want to have some mechanism we're able to generalize the knowledge from the states we already visited to those states we haven't visited so far. So people usually do this via so-called techniques called function approximation. Just remember in the tabular MDP, what we call it tabular just because we say this value function QSA, because we have small number of states and number of actions, we can represent this entire function QSA as a table, which is sized by S by A. On the other hand, for function approximation, we don't want to represent this by a table because this size of table is going to be enormous. What we want to do is we want to approximate this value by some function f in a given function class. And this function class is going to be complex, but it's going to be much simpler than this number of states. Usually people do this by deep neural networks. And this function approximation definitely going to introduce a lot of additional challenge compared to a tabular setting. The first one we already mentioned is about we have enormous number of states. And the second one, because now we kind of restricted our consideration of a value function into some function class, so every time we do this value iteration or we do this Bellman update, we're going to introduce some additional bias in the dynamical programming. We're never able to do the exact dynamical programming. And finally, as we said in the tabular setting, we eventually want to do exploration. And exploration actually heavily depends on you can estimate the uncertainty. And the way you estimate uncertainty, you need to discover the structure between those different states, which is going to be heavily relies on the structure of function f. To let you know how difficult is this function approximation, we can think of the very basic setting where we just do a linear function approximation. When people talk about linear function approximation, people usually just say, I assume a realizable case. That is, the value of my optimal policy, Q star, is going to be a linear function in some feature. And to be specific, that means I have some hand design feature, phi, that is for each state and action, I will map it into some like Euclidean dimension. And then my optimal value function is going to be factorized as an inner product between my features and some unknown like vector W star. So because we know the optimal value function is a linear function, of course we can just use linear function because we can just consider the function class of linear function because this is guaranteed to include this optimal value function. And this linear function, it turns out, is actually not bad for a lot of real application. For example, in this Tetris game, For a very long time, the state-of-art controller is actually just based on some handcrafted linear feature that depends on like how many holes I have and what is the height and how many pieces I have. And eventually the value is just the weighted sum of those features. However, although this is like already a very strong assumption, I assume the optimal value is a linear function. Still, there is absolutely no polynomial results for any algorithm for this setting, even till today. What makes it worse? There are even some related negative results saying this setting might be very difficult. So it's actually by a very recent work by Du et al., which is just saying if my optimal Q star is not exactly linear, but approximately linear, then for any algorithm, in order to find an epsilon optimal policy, you actually need exponential number of samples. So this story sounds very pessimistic. That kind of like saying, even if my Q star is somehow like approximately linear, then I cannot do anything. But in practice, we're still doing something reasonable about function approximation, right? So on the other hand, we can look at what is the algorithm people usually do in practice. So let's just think back. We just introduced the value iteration in a tabular setting, which is saying my Q value is equal to the rewards I receive immediately and the expected rewards I'm going to receive in the future. What's different in the function approximation is now, because my expectation is replaced by empirical expectation, the right-hand side of the equation is no longer guaranteed to be linear. That means if I apply this equation, I do value iteration, I'm going to end up with some Q-value function that is nonlinear, and eventually I lose out of the control about the function class. I want to restrict my function class to be a linear function. So in practice, there's a very simple fix to this problem. Instead of just doing this exact update, why not just do least squares, which is everyone use in the linear setting. So we just parameterize this Q-value function in terms of some linear function of psi and W. And then I just fit the least square of this problem. And I use that one to be my Q-value function. And this so-called least square value iteration is actually very good in practice, but there's no guarantees in theory. So we're kind of like wondering what is actually missing in this entire picture about function approximation in the reinforcement learning. This kind of like allow us to go back to re-examine the assumption we make about the optimal value function, which we say the Q star need to be a linear function. If we look at the optimal Bellman equation, we can see what do we mean by Q star as a linear function. That means Q star is actually just equal to the rewards and expectation of the future values. And the first term rewards is talking about rewards, and second term is talking about something transition matrix. So the original realizability assumption is really talking about the summation of the rewards and something about the transition is going to be linear. It does not say anything about whether the rewards is linear or not, or whether the transition is linear. It can be the case rewards is something very bizarre, very weird, and the expectation of the real value is also just something weird, but somehow magically summation of them just become a linear, which is a weak assumption, but we expect not to be that bad in practice. In practice, we expect the reward somehow has some structure, and the transition also has some structure. So the first try we can do is, why not just think of some case about, first we have linear rewards, which is very standard in the like linear bandit scenario. And the second one, we also just want to say the transition is linear. Just want to note, the transition linear is a little bit tricky. Actually, this assumption has been examined by a lot of prior work. The transition linear, exactly what we mean is for any value function we're going to consider in our algorithm in function class V, we have this thing is true. The expectation of this value function over condition on some state action, my current state action, is going to be factorized by some linear feature of my current state action, and some weight vector, which only depends on value and independent of my current state S and A. So this is going to be the new structure we're going to expect to hold in practice. That is linear rewards and linear transition, and in sum we call it linear MDP. And it turns out, even if we just expect those stronger assumptions, this strong assumption actually holds for a lot of real problems. The first one, tabular MDP, is just a special case of our linear MDP. And the second one, if we restricted the value function to those value generated by linear policies, this assumption also holds for the LQR problem, which is a very elementary control problem studied in the control community. And furthermore, it turns out this additional assumption, this linear MDP structure, is exactly what we miss between this theory and practice. So this is the recent results we're able to show. And this is joint work with Yang, Wang, and Jordan in 2019. And for linear MDP, under the assumption we just said, for linear MDP, this least square value iteration, and with some UCB, as we said, because we want to do some exploration, with some upper confidence bound, is able to find epsilon optimal policy within this number of episodes, that is d cubed h to the fourth over epsilon squared. And again, we emphasize this is no longer exponential in the horizon of the game. This is everything in polynomial, in the length of episodes and d. And what is the major takeaway of this work is now we actually have a very basic theory about linear function approximation, and more importantly, this is with a very clean algorithm, just least square value iteration with upper confidence bounds. And in the end, I also just want to place our work with some related works, and there are two works, Wen and Van Roy, and also Du et al. And they study some linear function approximation with some other assumptions. And just unfortunately, it does not hold for the general tabular settings. And there are two recent work, Yang and Wang, very good work. They did linear, they actually exactly started linear MDP, but with an additional further assumption on the simulator and additional assumption on the transition matrix. And finally, I also want to comment this final work, which was done by the group of Microsoft New York, which they actually able to study the general function approximation, and as long as they have low Bellman rank, which is a complexity measure. And this type of results actually apply to our setting, because our setting Bellman rank is not very high. And the good thing is they actually able to prove generically they can provide polynomial samples, but unfortunately the runtime is exponential. So our results is first results which deal with linear MDP with no additional assumption and has clean algorithm. And furthermore, we have polynomial samples and polynomial runtime. Okay, so finally I want to say a little bit about what is interesting, what I think interesting in the future. First thing, if you remember in our sample complexity for the linear function approximation scenario, we still depends on d to the cube, and which we believe in practice are like minimax rate may be linear in d or square in d. So the first question would be, what is optimal rates in the linear function approximation setting? And secondly, definitely more interesting is about now we have some theory about linear function approximation, how we're gonna go beyond this linear function approximation. For example, we can do kernels, we can do neural networks. I guess this is the whole point of this workshop. And I would hope there will be more results in the future. And this concludes my talk. Thanks.